Have you ever wondered how your phone just knows it's you? Or how those Snapchat filters stick to your face perfectly no matter how you move? Well, today we're going to pull back the curtain on the magic behind all of that. We are talking about computer vision, how machines actually learn to see. And trust me, it's way cooler than you probably think.
So let's kick things off with this big question. Think about it. We use facial recognition to unlock our phones every single day. We've all seen videos of self-driving cars navigating these crazy busy streets. But how does that actually work? How does a computer look at a bunch of pixels, literally just tiny colored dots, and say with confidence, yep, that's a cat, or that's a stop sign?
Well, the answer is a really special kind of AI brain that's built specifically for seeing. It's called a convolutional neural network, or CNN for short. And you can pretty much think of it as the AI version of our own brain's visual cortex. You know, the part that does all the heavy lifting to process everything we see around us.
Okay, so this diagram right here, that's the whole roadmap of a CNN. Now, I know, it might look a little intimidating at first glance, but I promise the main idea is actually pretty simple. You've got your image on the far left, let's say it's our cat, and then it flows through this series of layers that act like filters and processors, until bam, it spits out a final decision on the right. We're going to break down every single one of these steps, starting right at the beginning, finding features.
So how does a CNN even begin to see a cat? Well, it doesn't just recognize the whole animal all at once. Nope. Instead, it's kind of like a detective showing up to a crime scene looking for clues. It starts by spotting the most basic building blocks of an image. You know, the sharp edge of an ear, the gentle curve of a tail, or the fuzzy texture of fur. And this first, absolutely crucial step is called convolution.
The detective's #1 tool for finding all these clues is something called a kernel. And honestly, the best way to think of a kernel is like a tiny, super specialized magnifying glass. But here's the thing. Instead of just making things bigger, this magnifying glass is designed to find one very specific pattern, like a perfect vertical line or a sharp little corner.
Now here is a super important concept you gotta remember. To a computer, an image isn't really a picture. It's just a giant grid of numbers, like a spreadsheet. Each number just tells the computer the color and brightness of a single pixel. And our kernel? Well, it's also just a tiny grid of numbers. The real magic begins when we start to slide this small kernel over the big image grid, one spot at a time.
Okay, so as this kernel slides across the image, it's doing some pretty simple math. Imagine the numbers inside the kernel are like a secret code. When it lands on a part of the image, it checks if the pixel numbers underneath match its secret code. If it's a really strong match, it basically shouts, "Hey, I found something," and it puts a high number in a new map. If it's not a match, it just puts a low number. The result is a whole new image we call a feature map, which is basically a treasure map showing exactly where that specific feature, like a vertical edge, was found in the original picture.
And this is where things get really, really clever. By changing that secret code, the numbers inside the kernel, we can tell it exactly what to look for. If we design a kernel that's searching for a jump from dark pixels to light pixels in a straight vertical line, well, its feature map is going to light up and highlight every single vertical edge in the photo. And you can see that in action right here. You program a kernel with one set of numbers, and it becomes a vertical edge detector. Change those numbers just a bit, and boom, now it's a horizontal edge detector. What the CNN actually does is use hundreds of these different kernels all at once, creating this huge library of feature maps, one for every possible edge, curve, and texture it can find.
But wait, here is the most incredible, mind-blowing part of this whole thing. We don't have to sit there and design these hundreds of kernels ourselves. That would be impossible. Instead, through a process called training, we just show the network like thousands and thousands of cat pictures, and completely on its own, it learns which patterns are the most useful to look for. It figures out all by itself that things like pointy ears and whiskers are important clues for finding a cat.
Okay, so now the network has created dozens of these feature maps, and each one is highlighting a different little pattern. That is a ton of information. So the next logical step is to clean things up a bit. We need to summarize it all and focus only on the most important signals. And this step is called pooling. The most common way to do this is called max pooling, and it's a really simple but super powerful idea. The network just scans over the feature map with a little window, let's say 2 by 2 pixels, and in each of those little windows it finds the maximum value, the strongest signal, and it keeps only that one. You can think of it like reading a whole paragraph but only highlighting the single most important keyword. Now, this is brilliant because it does two really important things. First, obviously, it shrinks the feature maps way down, which makes the whole process faster and way more efficient. But maybe more importantly, it makes the network smarter. By just keeping the strongest signal from a small area, the network learns that the exact location of a feature isn't as important as the fact that the feature is there at all. A cat's ear is still a cat's ear, whether it's in the top left or the top right of that little window.
All right, let's get to the final step, the home stretch. The network has detected all the simple features. It's summarized them, and now it's time to put all those clues together and make the final call. Is this a cat, a dog, or maybe something else entirely?
So after a few rounds of finding features and then summarizing them, the network has this really rich set of processed feature maps. To make a decision, it does something surprisingly simple. It takes all of these 2D maps and just flattens them out, lining up all the numbers into one single long list. Think of it like taking a whole stack of papers and just laying them all out end to end. This long list is now a complete summary of all the important visual evidence from the image.
And this long list of numbers gets fed into the final part of the CNN, which is called a fully connected network. Now, if the first layers were the eyes, finding all the visual clues, this part right here is the brain. It looks at that entire list of evidence. It sees a high score for pointy ears, a high score for whiskers, and another high score for furry texture. And it learns how to weigh all that evidence to make a final call. The evidence strongly suggests this is a cat.
So let's do a super quick recap of the 3 core steps. First, you have convolution, which is using those kernels to find all the basic patterns. Then you have pooling, where it summarizes those patterns to focus on what's really important. And finally, classification, where the brain of the network looks at all the evidence and makes that final prediction. Easy enough, right? Okay, so we've covered the how, we know how they work. But what about the so what? Why should you actually care about any of this? Because, let me tell you, this isn't just some cool theory in a lab. CNNs are already out there in the real world, powering tech that is changing absolutely everything. Just take cars, for example. The most obvious one, of course, is in self-driving vehicles, where CNNs are the eyes that spot pedestrians, read traffic signs, and make sure the car stays in its lane. But they're also being used inside the car to monitor a driver for drowsiness, and even pointed at the road under the car, using cameras to spot potholes before you hit them.
And the power of these networks is it's incredible. Get this. One research team was trying to identify the tiny tips of plant roots in microscope images. Their old computer program was only about 70% accurate. Pretty good, right? Well, then they trained a CNN for the same job. Its accuracy, a stunning 98%. That is the kind of game-changing leap forward we're talking about with this tech. And the applications are just exploding everywhere you look. In medicine, CNNs are now helping doctors spot cancer in medical scans, sometimes even more accurately than a human expert. They're being used to translate sign language in real time from a video feed and to understand exactly what's going on in really chaotic, crowded scenes. The potential here is truly limitless. So, we've seen the building blocks, we've seen what's possible, but you know what? The most exciting part of this whole story isn't what has already been done, it's about what you are going to do with it. So I want to leave you and your teams with this one question. Just look at the world around you. What's a problem, big or small, that could be solved if a computer could see? Could you build a CNN that automatically sorts recycling? Or maybe one that analyzes drone footage to check if crops are healthy? Could you create an app that helps visually impaired people navigate a new city? The tool is here. It's powerful. And now it's in your hands. That's all for this explainer. Thanks so much for tuning in, and seriously, we can't wait to see what you built.